The paper of the day is Granularity of Locks and Degrees of Consistency in a Shared Database. This is a paper of two halves, connected by the common theme of locking. The first part of the paper examines the trade-off between locking overhead and concurrency. The second part of the paper examines the trade-off between consistency and concurrency. Granularity of locks. In the granularity section, the choice of lockable units is discussed. A lockable unit represents a section of logical data that is atomically locked during a transaction. Locking smaller units, such as individual records, improves concurrency for simple transactions that access a small number of records. On the other hand, locking at a record level can reduce throughput for complex transactions that require access to many records. The overhead of acquiring and releasing locks overwhelms the computation. It follows that having different sizes of lockable units in the same system is required to handle multiple use cases. Given this requirement, the paper presents a logging system that provides varying levels of log granularity for hierarchical data. In the example, a database is divided into areas. Each area has one or more files, and each file has one or more records. Locks may be obtained on any one of these hierarchical levels to provide concurrent access for transactional operations. Two types of locks are presented, X for exclusive locks and S for shared locks. Exclusive locks cannot be shared between transactions and are used for write access. Shared locks can be shared between the transactions and are used for read access. Requesting a lock on a node is in the hierarchy implicitly locks any descendant of the node as well. The main contributions of this section is methods for coordinating shared and exclusive locks between ancestor and descendants in the hierarchy. To do so, the notion of intention lock is introduced. Intention locks are implicit locks that are granted to an entire subtree of a lock. Thus, if you request a shared lock on a parent and an intention shared lock on all descendants of the parent is granted. Likewise, for X locks, in order to facilitate transactional locking, any two lock requests check for existing shared exclusive, intention shared, or intention exclusive locks and either acquire a lock if able or wait for a lock to become free. To safely acquire a lock requires checking existing locks for compatibility. For example, shared locks are compatible with other shared locks. Concurrent read-only access to the same data is allowed. However, exclusive locks are incompatible with shared locks. Concurrent read access to data that is being written is disallowed. Similar rules are defined for additional combination of locks and intention locks. This diagram presents the compatibility metrics of different lock modes. The paper defines consistency as satisfying all assertions on the data. Depending on the operation being done on the database, it may become temporarily inconsistent until a full sequence of operations has completed. As such, sequences of operations are combined into atomic transactions. It is the database's responsibility to ensure consistency at transaction boundaries. If transactions ran serially, then each transaction will have a consistent view of the data. Concurrent execution of transactions raises the possibility of reading inconsistent data. The paper defines four modes, degree 0 through degree 3. More recently, we would call degree 1 read uncommitted, degree 2 read committed, and degree 3 repeatable reads. Transactions are also defined as the unit of recovery. For example, after a transaction has been committed, you cannot roll back since other transactions may have already read the committed value. Degree 0. A degree 0 transaction is the least restrictive type. It promises to not overwrite data from other transactions. It requires having any transaction take a lock on any data it writes. Degree 1. Read uncommitted. Degree 1 consistency keeps the promise of degree 1, that is not to overwrite data, and also agrees not to commit any writes until the end of the transaction. In this case, you may require a longer lock that is held until the end of the transaction. Degree 2, that is read committed. Degree 2 consistency further restricts a transaction to only read values that have been committed, in contrast to a degree 1 transaction that may read dirty values. In addition to acquiring locks for all data written during the transaction, a degree 2 transaction acquires locks for all data read during the transaction. A degree 2 transaction may still read two different values, both committed by different transactions, if it reads the same entity twice. Degree 3, that is repeatable reads. Degree 3 consistency completely isolates a transaction from each other. It requires long-lived locks on both read and data written. Degree 3 provides the highest level of isolation described in the paper.